Hello everyone. Thanks a lot for coming over here. Welcome to a day-long symposium on recent cosmology results from DESI and eROSITA. So we'll start by our first talk, a short introduction to long path of DESI and eROSITA by Subha Majumdar from TIFR Mumbai. He has been there for more than a decade and have a lot of experience working with large-scale structure from its early days, particularly on galaxy clusters, CMB secondary anisotropy, and dark matter modeling. So today he's going to give us a glimpse of how the large-scale structure history, both observation and theory evolved, and how we are today in terms of the current status of the field. Shubha.
Okay, thanks a lot, Shadab. So, as the title suggests, this is a short introduction to the long path, and the main thing is both of the words are important, the short and the long, because the path to DESI and eROSITA started almost maybe 50 years back, maybe 30 years back, depending on how you want to look at it. And the idea was before one jumps into the real technical talks, this will be like a teaser. I mean, it's more like a storytelling because it's sort of a history. And so there is nothing complicated in this 20 minutes. Although when I started working on this, I realized that it's actually in 20 minutes, it's very difficult to do this. So that was really difficult. So I didn't know what to say or what not to say. Okay. So let me start at the very beginning. So on a dark night, not in Bangalore or Bombay or anywhere, probably most of the cities in India, if you really go to a dark night and look at the sky, then you can see stars and you can count stars by looking at it. And typically, people have counted 5,000, 6,000 stars. That's the number of stars that you can count on the sky. But stars are, of course, in the Milky Way. And what we see is, of course, the brightest thing, which is the moon. And so this is the size of the moon. It's half a degree. But if we take a photograph of the similar area, then at 20th magnitude, it's like 1,000,000 times fainter than what we can see, we'll see lots of galaxies. Okay. So once people started taking photographs, it was possible to count galaxies. That's the first thing. So previously, by naked eye, we could count stars. Once we started taking photographs, we can count galaxies. Of course, this is an old photograph. If you look at the Hubble Deep Field, it has many, many, many orders of magnitude more than this. Okay. So people really started doing it. When they first started taking photographs of the sky, and this is in the 1950s, Shane and Wittonen, they spent 10 years of their life looking at photographic plates and counting galaxies and pointing it somewhere in a piece of paper and looking by eye. And they looked at 1,000,000 of them, basically, in 10 years. And when they pointed out, this is the really first large-scale structure of the sky. Okay. And you can already see things which we are sort of familiar now. This filamentary nature. Okay. These things are like some filaments, there are some overdensities, lumps, there are voids and stuff like that. But it took another 30 years before you had enough instrument sensitivity that you can look at one strip and get redshifts of these objects. Once we get redshifts of these objects, one could connect to background cosmology. Now, in between 1950s and 1980s, two big things happened, which basically gave birth to the way we do modern cosmology, at least in today's talk. One was, oh, by the way, once we look at these things, when you look at these redshifts, you find all these structures, these great walls, voids. I'll come to this later. This was 1980s. So first is, this book came out by Peebles, this large-scale structure of the universe. And over here, he had this entire large chapter into how to do statistics with galaxies. So you do statistics with galaxies. You basically look at their endpoint correlations. Mainly we do a 2-point correlation, that's easy to do. 3-point is very difficult to do, even in terms of calculations. And these statistics can be connected to underlying theory of structure formation. That was the basic idea. Okay. So this what has led to everything that we'll see in BAO today. We'll have to do statistics somehow. The basics were laid out over here. Things have changed over the years, improvement has happened, but the basics are all over here. And once you do the statistics, there is a way of connecting it to your background cosmology. So this came out in the early 70s. In the mid 70s, another paper came out, this paper by Presch and Schechter. Actually, they did one of their first n-body simulations with like 1,000 particles. Think of n-body simulation with 1,000 particles. We do it with billions and billions of particles now. And they've realized that if we start with some Gaussian random fields, then these particles, due to gravitational attraction, they move and they coalesce. And if I can count the objects, then they have the number of objects of a particular mass. If I count that, it has a very simple form, which now we do by big simulations and fix it in the fitting function. But the simple form can be just calculated, derived by looking at a Gaussian random field and integrating it over some overdensity, saying that things will collapse if things are over overdensity. Okay, and that sort of looked like this. So if I look at this, is think of this as this is mass over here, and think it over as the number of objects of particular mass, okay, at different redshifts. And you see, this is of course not from the simple calculation Presch and Schechter, this is from simulations, but it's beautifully fitted by some functions. So I have not written the function over here, but one simple function with some parameters fit all these plots. What is important is two things. First, this happened because in simple theory, you can take a Gaussian random field and integrate all collapsed objects over some threshold density contrast. And the interesting thing is that when you go to these large masses over here, you see things fall very fast. So just like in the previous case when you had galaxies, their correlations depending on what kind of cosmology was there. Over here, what one can do is that for these larger masses, the numbers are really, really exponentially sensitive to what the cosmology is. So because we're looking at clusters of galaxies in this mass range, a little bit change in cosmology changes this thing. So that's why this led to thinking that, okay, we can look at clusters, we can count clusters, and basically translate it to cosmology. Y-axis is the mass functions, it's the number density per unit volume. Now, of course, this is an interesting plot. It's seldom showed, and for people over here, you know that all these things we know that it started from Gaussian random fluctuations, and in CMB, of course, you see these beautiful plots of CMB perturbations, CMB anisotropies, and you can plot a histogram of CMB anisotropies, and it's very Gaussian. But in large-scale structures, we showed that there's filaments are formed. Question is, this is done. This theory comes from Gaussian. How valid it is? This is actually a distribution of fluctuations in the large-scale structure. Okay, and over here also, to first order, it's very, very Gaussian. Now, of course, I'm not going to explain. This is not exactly the way it's done over here. It's not exactly just looking at perturbations, but it's done with some technique called Carnot and Lewis eigenvalue vectors. But anyway, even in large-scale structure, it's Gaussian. So it's not only CMB. So we must have seen CMB plots, but in large-scale structure, is it? So when the SDSS first came out, this was one of the most beautiful plots that I really looked at it and like, wow. You never think that in SDSS, when you look at all the structures, you can see Gaussian in the perturbations. Okay. Something also happened during these intervening years. We realized that once we have maps of CMB, and if we have a theory which connects large-scale structures, which are starting from the perturbations that we see in CMB, then we can connect these two. And of course, these connections have become better and better with really large-scale simulations. So this is a map. This is actually a W map of the CMB. So it's not the Planck map, doesn't matter. One can take these perturbations in the photon field find the relative perturbations in the matter, and then evolve those perturbations. And people do it in large-scale structures. You have seen these pictures many, many times. So you can start with this similar kind of perturbation in large-scale structure at very large distances or very early universe at high redshifts. So this is typically started at redshifts of 50, 100, maybe depending on what is your capacity to do it, but maybe even at redshifts of 20. And then this is again from the Millennium simulations. There are better simulations now, but doesn't matter. So you start doing it and you evolve it over time, and it sort of evolves. So this is basically only dark matter. So anything which is white is a dense over density, which is dark over here is an under density. It's all dark matter. So it basically changes and changes. So it starts with this and finally becomes something like this. Okay. So over here you can see the dark matters have collapsed. This is what the pressure sector formalism with this 1,000 particles has said. In sort of clumps over here, everything which is a little over density is slight white spot, and there are sort of empty regions over here, and it has a filamentary structure, and famously got the name of a cosmic web because it looked like the web of spiders. Okay. Now in the 1970s, the late 1970s, sort of emboldened by the fact that we can look at this kind of filamentary structures already, and there were already hints in simulations, people started doing spectroscopic surveys. So not only photometric surveys, because otherwise you do not know the distances, you cannot really resolve because in photometric surveys, all these things will be collapsed, and these structures will be sort of erased, okay? And not only counting on the sky, of course you could look at on the sky, but then the structures are erased, the spectroscopic surveys. And so this was what they did. Okay, so let's go. So this was one of the first surveys that happened during 1978 and 1982. So that's like 82, so it's 40 years back. And as you can see, this was not just counting objects in the plates. People had spectra for these objects and a slice of the sky, and we can already see some structures. This is actually the coma cluster. The coma cluster, you can see over there, and the colors are for two different kinds of galaxies, red galaxies and blue galaxies. Red are the old galaxies, blue galaxies. And you can see we really found something which theory has predicted. Because of local velocities, you will have clusters in the redshift space, it will be elongated, and there's this finger of God effect over there. So this happened in the 1970s, 70, 82. This is called the CFA1. And very soon people did the CFA2, which was like amazing, 18,000 objects with redshifts. Now, you should remember these numbers, 18,000 objects, when you think of the numbers that people will say today, which is millions. That's the progress that has happened over here. And this was this famous CFA2 slice, and you can see again, there was a coma cluster over here, there's a great wall. But something you can see over here is that you are only looking at the very local universe. So the CFA2 went to around 0.035, 0.04 in redshift. That's very, very close by. So coma cluster is over here. Coma cluster is very nearby. Okay, so it didn't really go. But this gave a boost. So this basically says that we can do large redshift surveys. So this led to the first large, really large redshift survey, which was the SDSS. Okay, it's a large area of the sky. And similarly, this was a US-based effort, and similarly there was a UK-based thing, which was called the 2DF. Okay. So one thing people realized that now we can actually compare this kind of maps with this, and so one can do cosmology with it. So immediately, as I said, because emboldened by the fact that you can do this kind of surveys, there was proposals to have bigger surveys. So there was the 2DF survey, something called the 6DF survey. The SDSS is the first generation of really large surveys. And when the SDSS first results came out, you can see how much it increased. So this was the CFA slice. This was the extent of CFA. And this was the extent of the SDSS, the first SDSS. So suddenly we had thousands and tens of thousands, it was 100,000 class objects in the sky to high redshift, from which we can do really statistics, okay? And those statistics can be compared with theory. Okay. So this is the real SDSS map. It came out in like 2000, close to. It's a really spectacular map of SDSS. It's galaxies and agents. Okay. So as you can see, the CFA survey was this region. The SDSS goes all the way up to 1 point. Okay. Now, I mentioned that CMB and large-scale structures are connected, and that gives us a big boost in our game. Because if we want to do cosmology, it's better that whatever underlying background cosmology we have or theory we have, it gets explained by both CMB and large-scale structure. And if it does, then we can sort of combine those two experiments to give good results. And so when the SDSS results came out, they could actually do it. At that time, WMAP results came out. And so this is a theoretical curve, okay, of density fluctuation as a function of, it's basically made for popular audience, so it's in millions of light years, not in megaparsecs or so. But density map as a function of size. So density goes down, over density goes down as the size increases. And you can see this region is proved by CMB, and the regions which is proved by clusters, by galaxies, lensings, intergalactic medium, and all of them, these are all different experiments, completely different experiments, completely different systematics. All of them fall roughly on this curve. That itself is spectacular, that it tells you that one underlying theory of the universe basically explains CMB and different large-scale structure probes. Today, we are only going to look at cluster probes and this galaxy clustering. Okay. A later plot after Planck gives more points, better data, and the map, this fitting is even better. Is really, really good. Now, if you look at this plot, you will see that if you look very carefully, it is not a straight line over here. There is some undulations over here. These undulations were there in CMB, and I will come to that. And these are what is known as baryonic acoustic oscillations, which is what will be a whole talk today morning. And this is what is the main thing that DESI has come up with. The reason is, if we look at power spectrum of fluctuation in theory, and look in terms of different cosmologies, so these are different cosmologies. So some ratio of baryonic density to total density, dark matter density, and take away the initial perturbations, then depending on the amount of baryons to dark matter, you have this kind of oscillations. Okay. And I will explain why these oscillations are there in the power spectrum. Okay. And if these oscillations, this is in the early universe, and if these oscillations persist, then this should be there later also. And this is seen in the CMB, so this is quite early. And if you can look at these oscillations and look at the amount, then you can actually tell, okay, this must be the ratio of baryonic matter to dark matter. And depending on the scales, so there is a scale KQ, there's K silk. I mean, I'm not going to explain the scales, but these are all depends on cosmology. So from here, from this, when the radiation and matter energy density were comparable, that fixes a scale. When silk damping happens, that fixes a scale. All these things, scales and these oscillations now go into the physics, which goes into this cosmological parameters. And as I said, I mean, this is more of a storytelling, so I'm not going to go into, but you can ask me questions after this and I can explain. Okay. So this was the CMB map, and you are familiar with this picture, most of us, I guess. I mean, I think everyone over here. This is a fluctuation. So this is a power spectrum, okay? So this is basically a redrawing of this. So this is the primordial fluctuation in the radiation. And this is what you see in the CMB. What we do not talk a lot about is that similarly at the time of CMB, just like there is a primordial fluctuation spectrum in the CMB, in the photons radiation, there is also the same kind of fluctuation in the matter, okay? And you can see there are these peaks and troughs also corresponds to peaks and troughs. It's slightly shifted. There's a reason for that, but you have peaks and troughs in the matter. Now, these are the matter which, as I told you, give rise to galaxies. So in galaxies, if we can try to measure this, we should be able to look at these peaks and troughs. And remember, these peaks and troughs correspond to these peaks and troughs. So if you know what is the co-moving size of, for example, this peak, then I should be able to predict the co-moving sizes over here and look at these co-moving sizes at different redshifts, and then we can say how the size is changing. And the change of sizes, of course, depends on the cosmology. That's the basic idea. So let's go into a little more detail about this. So probably Nikhil will show this picture. This is a very, very beautiful picture from Eisenstein's CO on white paper. It tells us what happens. It's one technical picture over here. So think of early universe where you have dark matter, you have photons, you have baryons, and you have neutrinos, and there's a perturbation. So think of a point perturbation. A perturbation, the perturbation sort of spreads, okay? You can solve a Green's function, okay? Sort of spreads. Now, the photons and baryons are coupled with each other. So, over here, after a little bit time after the perturbation started, there's a dark matter, which is still at the center because the dark matter, does not have a pressure, it's pressureless. But the photon and baryons are coupled, and the photons are driving, and the baryons are going away with it. So the photon-baryon perturbation moves ahead. So this is in size, okay? The neutrinos are decoupled. So neutrinos free stream away, so you can see the perturbation is already dying. So this is at some very high redshift. By the time of recombination, when the photons last scatter, the dark matter is somewhere over here, still at the center. The photons and baryons have moved quite a far away. The neutrinos have almost become like a background neutrino density all around. And as you can see, it has sort of reached a peak around 100 megaparsec, a little 105 megaparsec. And at this time, the photons and baryons decouple, okay? Once the photons and baryons decouple, the photons free streams, the photons behave like neutrinos. So at later stages, the photons are behaving like neutrinos. So neutrinos are becoming as a background. The photons are also free streaming. The baryon has a peak. The baryon is left over there because baryons have been dragged over there at these distances, this perturbation. It is no more coupled to photons, it's left over there. These baryons, because it has some mass, have dragged some of this dark matter towards it. So you can see the peak has moved a little bit. Late time, when these galaxies are forming, the photons and the neutrinos are sort of completely background. The baryons is over here, but some of the baryons have been dragged back a little bit over here, okay? And the dark matter, because the baryons are over here, also has a little bit of spike over there. And remember, the galaxies are formed where there are overdensities. So there will be an overdensity of objects around this region, okay? So you can think of it in this way again. Again, this is from the Eisenstein. It's a very nice picture. So we have these perturbations moving, and there is a scale which is set. This scale is set in the CMB. We know you can measure the scale, and you can measure the same scale from correlation function measurements of galaxy distribution, and we can compare these two radial scales, okay? The problem is that, of course, it's not one perturbation. There are to think of raindrops falling on water. There's a lot of circles, and you have to find the scale. So, of course, you can do the correlation measurements and get the scale this size. But another easy way to do is to do the Fourier transform, and the scale comes out as the frequency, okay? So here was the first spectacular. So doing this thing, what I said, was the first spectacular detection of BAO. This was predicted. If the theory of cosmology that we are doing was right, then they should see this bump in the correlation function. And lo and behold, they saw this bump in the correlation function. It's a small bump because it is basically depends on, this wiggles depend on, as I showed before, depends on the ratio of baryon to matter. So a small bump. So this is over here, it's multiplied by this co-moving distance squared. So there's this bump. And a nice thing you see over here, the three lines, these three lines correspond to three different cosmologies. So immediately you can see that one of the cosmologies will fit this bump better. So if you can get the bump, you can get the cosmology. This was in the real space. In the Fourier space, you find this beautiful thing by combining SDS and SDSS, these oscillations. So this is this BO wiggles that you saw in CMB. The CMB had these wiggles, and exactly the same wiggles that we're getting in BO. So this was a very big discovery in cosmology. It came out in 2005. 6DF came out like a year or two later. They saw the same bump. So now every large-scale structure survey were routinely getting VO bump. The idea was to make it better and better, improve the theory and improve the, so observation will reduce this error bars and theory will tell you how exactly to measure this bump because we need to know exactly the scale, okay? So if the bump is sharper, can we make it sharper or not? Now, one thing you should see over here, this SDSS or 2DF, these are even though it was bigger than CFA, it's still low redshift. But emboldened by SDSS and 2DF, there were proposals which wanted to do it at high redshifts. So the first of them was this thing called Wiggle-Z, which came like 10 years later. And see, they have got this bump at 4 different redshifts. So this is at this low redshift, 0.4 to 0.8, 0.6 to 1, 0.2. So they have this Wiggle-Z bump at different redshifts. So now what they can do is they can look at how the scale changes with redshift. So here was the 6DF result that I showed before. This was an SDS LRG, this is Wiggle-Z papers. So now your cosmology should be such that should pass through all the scales. So that scale should move according to whatever is the best fit cosmology. And that is how we do BO cosmology even now. Okay. One interesting thing is that look at how powerful it is when compared to supernovae. So when the Wiggle-Z came out, this was the Wiggle-Z points, and this was the supernova points. 1,000 supernova points, and 1, 2, 3, 4, 5, 6 Wiggle-Z points. We get almost very close similar cosmological combinations. Okay. Next decade, 2015, more. So from SDSS, they were SDSS 3, SDSS 4. They were called, Baryon Acoustic Oscillation Survey BOS, the extended Baryon Acoustic, extended, right? I think EBOS, then there was the DS, and all of these led to this very, very precise determination of the wiggles in the Fourier space and the bump in the configuration space. And this picture that I showed you over here, see how this picture improved in the next 5 years with all these surveys. So look at the error bars now. So error bars are small. So you are very, very precise now in really finding the cosmology that you want to do. So this was still, let's say, the 20s. By this time, of course, people were emboldened that they were getting these very, very good constraints on, and I'm putting up these constraints because today, I'm sure DESI will talk about the neutrino constraints and the constraints on dark energy because those are 2 important results that have come out. They already had beautiful constraints and they wanted to make it better. Let us not go into the details of these constraints. And so the DESI thing was put up sometime in the middle of 2016 or so, I think, where this DESI survey was decided. They basically said that we want to have more number of objects and we want to go deeper. That was the basic idea, and that's what it was. So they had BOS and EBOS, which is over here, and this DESI, which goes large radius, and also deeper. Okay, so this is, and of course there are some other surveys coming up. And the promise of DESI was that they would do spectacularly in dark energy, in the mass of the neutrinos, all the other cosmological parameters. You may try to remember this page or look it up later and see how much they have kept their promise when they have showed their first results. Okay, so that's about DESI. One thing you should realize that this results was in late 20s. This has come a long way from this first SDSS results. The first SDSS parameter measurements were like this. This was the kind of measurements. But even then, we had whatever we could do with CMB alone, just adding large-scale structure gave a lot of improvement. So there's a huge improvement that happened in the last 20 years. Okay, let me in 2-3 minutes, I've spent most of the time on BAO, go to cluster counts. Okay, because that's what eROSITA is the other thing that we're going to talk about. So this was the large-scale structure. If you look at these overdensities, these are clusters of galaxies. Okay, and the idea is we want to count their numbers because I told you in the very beginning, those numbers are exponentially sensitive to cosmology. Okay, so you want to count their numbers. If the number is 1,000, it means one cosmology. If the numbers for the same volume is 800, it means a completely different cosmology. Okay. And the idea is that if you want to be really count these clusters, because clusters are big objects, we need really large volumes. So we need to go bigger and bigger volumes, deeper redshifts, and we want to count more numbers, so slightly go lower in masses. Okay. That is the objective of any cluster cosmology. Okay. So number counts in clusters doing cosmology has been in the theory for 40 years now. However, not much has happened. Okay. One of the reasons, as I told you, as you can see, if you change a little bit of sigma or omega matter, the numbers change a lot. So it's very easily differentiable. With the dark energy, it's even more interesting because compared to a fiducial lambda-CDM model, if you change your dark energy, it changes in two different ways in low universe, low redshift universe, and high redshift universe. So it's very different from all the other kinds of cosmological measurements. So if you can do a cluster count very precisely, it's very, very promising for dark energy. Okay. And that was one of the push for cluster counts. But as I said, not much has happened in doing number counts because it's difficult. The first number counts was done quite back. So this was, hold on. Yeah. So the first ever cluster count happened in 2006. That was almost 20 years back. It was done with only around 1,000 clusters in a redshift range of 0.2 to 0.9 and only around 100 degrees on the sky, actually less than 100 degrees on the sky. And this was the number as a function of redshift that we got. So this was something that I was involved in, of course, and we got some parameter constraints. These were the first results that came out were counting numbers of clusters. And it showed that cluster counts actually works because the parameters that came out was agreeing with everything. We could do something called self-calibration over here. But from 26 till eROSITA, there has not been much with doing cluster counts. Okay. I'm going further. So it was already evident when the red sequence numbers were there that if we can do a really large survey, then we can get really big benefits. So our first proposal of our full sky cluster survey was proposed to NASA. It was called the DUET survey. And the idea was that we'll get 100,000 clusters all on the sky, 100,000 clusters, not like a 900,000 clusters over the sky. And with 100,000 clusters with large volume, the scope of the survey was really large. So this is something that, again, I was part of it. NASA did not, at the second level, the third level, it sort of did not go through. They canceled extra surveys saying it is too expensive. So then it was left for the Europeans to come up with their own survey. So the eROSITA was the exact follow-up of these numbers, 100,000 clusters. So over the time, people have realized that we should go to larger and larger areas in the sky and deeper. So the idea was that these were all the different small cluster surveys, like deep but very small, 1 degree in the sky, half a degree in the sky. We wanted to go to an all-sky region and sufficiently deep, not like this, sufficiently deep, so we can get 100,000 clusters. So these parameters were chosen that we do 100,000 clusters. And this is what eROSITA said, that we are going to get this really large number of clusters, different masses, basically looking up all the clusters few times, around 10 to the 14. So over here, if you look at this, the ultimate cluster survey would be to have a survey which will count every object over 10 to the 14 solar masses. The aim of eROSITA was to get as close as this. So that was what it is. It said that we'll get clusters, which is almost all the clusters over few times 10 to the 14, X-ray clusters all over the sky, and that will give you 100,000 clusters. And the promise was that if you receive all these massive clusters, and we can do, so this was the eROSITA handbook, you can do cosmology to a very, very precisely, okay? Especially with, basically, with statistics of clusters, number counts, we can do exactly what BAO that galaxy people have done, we can do BAO with clusters and things like that. Unfortunately, eROSITA, the results that we'll see today, doesn't have 100,000 clusters because of the Ukraine war. It was a Russia-German collaboration, so the collaboration fell apart. The satellite is still in the sky, it's not taking data, it's just wasting away. But for the first numbers are out, And so this is where I hand over to DESI and eROSITA to tell what exactly they have found after this 40 years of cosmology with large-scale structure. So I'll stop over here. I think I've already gone over time. Thank you.
We can take some quick questions if there is. Otherwise, we can move on to the next speaker. So next speaker is online. Can we sit down? Okay. Yeah.
This sector. How will the cluster counts
Pressure
matches
sector
with
is a
the...
very, so pressure sector has theoretical problems. And pressure sector is very simplified. You take a Gaussian random field, and as soon as your perturbation sort of goes above a critical number, this critical number comes from spherical collapse, okay? Then you count that to be falling into becoming an object, okay? First of all, we know that the collapse is not spherical, so that number should be changed. Number two, pressure sector has this problem of what is called counts in count. So, something which has fallen to a smaller object, at some later point will go inside a bigger object. So we have to sort of match that also. So it's better to do it in simulations. So people do a better and better and better simulations. And it matches well at this large mass limits. At small mass limits, there are problems.
So is pressure sector ruled out? Or?
No, don't use pressure sector. Use fitting formula from simulations. That's it. Pressure sector tells you that it should be like this. The basic form should be like that.
Yeah. So you're yeah. So is there a cosmology result from head-to-X? Maybe it will be discussed later. I think the slide said start time is 2014.
I don't know. I have not seen much from head-to-X.
So instead of cluster counts, you can also do LRG counts, right? Because that would be tracking clusters.
Yes, you can do LRG counts. Of course, as you know, with LRG counts, you have to have some kind of halo to LRG mapping.
That's reasonably well constrained.
That's reasonably well defined. In fact, one of my proposals was to do very similar thing with AGN counts.
Okay.
Similar things, similar masses, halo to, and use your halo distribution along with some numbers. Priyanka did it, and probably it will be done with eROSITA. eROSITA doesn't have any cosmology team working on AGNs, unfortunately,
Okay.
as far as I know.